The Earth 4 billion years ago was beginning to recover from the battering by celestial bodies that accompanied its violent birth. It had cooled sufficiently for water to condense on its surface. Islands were rising in the primeval oceans and starting to merge into continents. The lands were barren and the water lifeless, but the scene were far from calm. Still in the throes of intense volcanic activity, the young Earth was pitted by red hot craters spewing thick clouds of dust and fumes. It was ravened by deep cracks through which water seeped down to the molten core, later to erupt back up again, pressurized, superheated, and laden with vapors extracted from the seething lava. Think of Yellowstone National Park or of the Solfataras of Sicily, the Hekla region in Iceland, the flanks of Mount Fuji in Japan, or the hot springs of Rotorua in New Zealand. One memory invariably comes to mind: the smell, the all-pervasive stench of rotten eggs, the characteristic odor of hydrogen sulfide. Indeed, there is even likelihood that the cradle of life reeked of hydrogen sulfide. This fact has rarely been taken into account in origin of life scenarios. It deserves to be. There was no oxygen in the atmosphere around the Earth 4 billion years ago. Free oxygen is a product of life. This is as close to certain as anything can be in science. In consequence, the state of many minerals was very different from what it is today. This is particularly true of iron. Leave an iron object outside for some time and it turns to rust, which results from the interaction of iron with wet oxygen. There was no rust, there is no iron oxide on the prebiotic Earth. Instead, iron was abundantly present in the oceans in a form called ferrous. That is not found today because it would react immediately with atmospheric oxygen. The composition of the primitive atmosphere is still the object of debate. The prevalent view for a long time, popularized by celebrated Uri Miller experiment, was that the atmosphere consisted of hydrogen, methane, ammonia, and water vapor, and thus was very rich in hydrogen. This is now seriously doubted. According to many experts, carbon was probably not present in combination with hydrogen, but with oxygen. Nitrogen most likely existed as molecular nitrogen or in one or more of its associations with oxygen, not as ammonia. Traces, at most, of molecular hydrogen were present. If these new estimates were correct, the source of molecular hydrogen were present. The hydrogen needed for the formation of the first biomolecules raises a serious problem. Damn. Another problem we encounter when looking at the prebiotic scene concerns phosphorus. This element in the form of phosphate is a conspicuous constituent of many important biomolecules, in particular nucleic acids. The fact is surprising since phosphate is hard to find in the present world, at least in solution. The Earth contains plenty of phosphate, but locked up in water-insoluble calcium phosphate, the constituents of the mineral apatite. In marine and fresh waters, the concentration of phosphate is very low. Indeed, its availability is often a limiting factor in sustaining life in this environment. This was made clear when phosphates were added to cleaning powders. Contamination of lakes by phosphate containing waste water led to eutrophication, an excessive proliferation of algae nurtured by the newly available phosphate, which alters the food chain in such a way that oxygen becomes scarce and animal life severely hampered. How the rare phosphate molecules turned out to play its central biological role is an intriguing question. A possible answer to the problem could be acidity, a physical property that is associated with sourness when mild. Think of vinegar or lemon juice, and with bitingly corrosive powers when strong. Think of aqua fortis, used in etching, or vitriol sulfuric acid, the favorite weapon of betrayed Victorian ladies. Apatite readily releases phosphate when exposed to even a mild acidic medium. Perhaps the primeval waters in which life originated had this property. What was the temperature of the prebiotic world? Little solid evidence is available. This is unfortunate because temperature is a critical parameter that severely limits the lifespan of relatively fragile biomolecules such as proteins, nucleic acids, and many of the building blocks. With this fact in mind, many chemists concerned with the origin of life have opted in favor of cold environment even below freezing point.